This is the first of a series of videos on programming language semantics, and in particular on the semantics of cool. Before we dive into the technical details, though, I wanted to spend a few minutes talking about what programming language semantics are and why we need them. The problem we have to address is that we need some way to say what behavior we expect when we run a cool program. So for every kind of cool expression, for everyone, we have to say what happens when it's evaluated. And we can regard this as the meaning of the expression. We somehow give rules that specify what kind of computation a particular expression does. And I think it's useful to look back and see how we dealt with this, with similar problems in defining other parts of cool, okay, the earlier things that we've looked at in this course. So for example, for lexical analysis, we defined a family of tokens using regular expressions. And for the syntax of the language, we use context-free grammars to specify the structure of how words could be strung together to form valid sentences in cool. And then for the semantic analysis, we gave formal typing rules. And now we're to the point where we have to talk about how the programs actually run. And so we have to give some evaluation rules. And these are going to guide how we do code generation and optimization. They're going to determine what the program should do and what kinds of transformations we can do on programs to make them run faster or use less space, or any other kind of optimization that we would like to perform. So far we've been specifying the evaluation rules somewhat indirectly. We've been doing it by giving a complete compilation strategy down to stack machine code, and then we've been talking about the evaluation rules for the stack machine, or actually translating the stack machine code into assembly code. And that is certainly a complete description. You can take the generated assembly code and go and run it on a machine and see what the program does, and that would be a legitimate description of the behavior of the program. And the question then is, why isn't that good enough? Why isn't just having a code generator for the language, why isn't that already a good enough description of how the code is supposed to be executed? And the answer to that is maybe a little hard to appreciate without having written a few compilers. But in a nutshell, people have learned through hard experience that assembly language descriptions of language implementations have a lot of irrelevant detail. There's a lot of things that you have to say when you give such a complete executable description that was not necessary to say about how the program executes. So for example, the fact that we use a stack machine, that's not intrinsic to the implementation of any particular programming language. There are other code generation strategies that we could have used. So, the fact you don't have to use a stack machine to implement the language. Which way the stack grows, whether it grows towards high addresses or low addresses, you could implement it either way. The exact representation of integers, the particular instructions that you use to execute or to implement certain language constructs. All of these things are one way, or one particular way to implement the language, but we don't want them to be taken as the only way that the language could be implemented. So what we really want then is a complete description, but one that is not overly restrictive, one that would allow a variety of different implementations. And when people have not done this, when people have not tried to find some relatively high-level way of describing the behavior of languages, they've inevitably gotten into the situation where where people just have to go and run the program on a reference implementation in order to decide what it does. And this is not a very satisfying a situation, because often the reference implementation is not completely correct itself. It'll have bugs, and there'll be artifacts of the particular way it was implemented that you didn't mean to be part of the language, but because there's no better definition, wind up becoming fixed and sort of accidents of the way the language was implemented the first time. So there are many ways to actually specify semantics that would be suitable for our task, and it turns out that these are all equally powerful, but some of them are more suited to various tasks than others. So the one that we're going to be using is called operational semantics. So operational semantics describes program evaluation via execution rules on an abstract machine. We just give a bunch of rules that say, for a particular expression, how it should be executed. And you can think of this as a very, very high level kind of code generation. And this is most useful for specifying implementations, and it's what we're going to use to describe the semantics of cool. I want to mention two other ways of specifying programming language semantics because they're important, and you may come across them at some point outside of this class. One is denotational semantics, and here the program's meaning is actually given as a mathematical function. So the program text is mapped to a function that goes from inputs to outputs, and this function is an actual function that exists in the mathematical sense, and this is a very elegant approach, but it introduces complexities in defining an appropriate class of functions that we don't really need to consider for the purposes of just describing an implementation. And another important approach is axiomatic semantics, and here program behavior is described in some kind of logic. And the basic kinds of statements that you write in this language, or in an axiomatic semantics, is that if execution begins in a state satisfying X, then it ends in a state satisfying Y, where X and Y are formulas in some logic. And this is a very common foundation for systems that analyze programs automatically, that try to prove facts about programs, either to prove that they're correct or to discover bugs in programs.